Now, the groups of transformations. Okay, the groups of particular interest to a physicist are the groups of transformations such as rotations, reflections, permutations, translation, etc. of a physical system. Okay, so a physicist is more interested in groups of transformations of a physical system. The transformation can be brought out by rotations, reflections, permutation, translations, etc. Okay. Now, the symmetry transformations. The transformation which leaves a physical system invariant, that is called a symmetry transformation of a system. Okay, a transformation which leaves a physical system invariant is called a symmetry transformation of the system. Okay, so the transformation we know, rotation, reflection, permutation, translation, etc. These are called the transformations of the system. So what is symmetry transformation? A transformation which leaves a physical system invariant. Okay, the system remains same. Before transformation and after transformation we have the same system. Then we say it is a symmetry transformation. For example, a rotation of a circle about an axis passing through its center and perpendicular to the plane of the circle. That is a symmetry transformation, because if you rotate the circle about that axis at any angle, the circle remains the same. Okay, there is no change. So we say it is a symmetry transformation. Now, a permutation of two identical atoms in a molecule, that is a symmetry transformation for the molecule. Suppose a molecule is formed by two identical atoms, for example O2. Two oxygen atoms are identical, so if you interchange the oxygen atom, change their positions, interchange their positions, there will be no change in the system. So that is a symmetry transformation. Okay. Now we shall now we are going to show that the set of all symmetry transformations of a system is a group. Okay, so we are interested in the transformations of a system, and we are more interested in the symmetry transformations. Symmetry transformations are transformations which leave the system invariant. Now, the third point, the set of all symmetry transformations of a system is a group. Okay, so in the first class we had defined the group. Now we are going to say, or going to prove, that symmetry transformations of a system is a group. Okay, so first we will see that two symmetry transformations of the system, if we perform it successively. Okay, if we perform two symmetry transformations of the system successively, the system remains invariant. Okay, the system remains invariant. Thus, the composition of any two symmetry transformation of the system is again a symmetry transformation of the system. Okay, so the set is closed under law of successive transformation. We know a group has a law of composition. The law of composition here is the law of successive transformations. So the composition of any two symmetry transformation of the system is again a symmetry transformation. That we will see with an example. So the first property, we know for a group to be, for a set of elements to be group, it has to be first distinct. All the elements of the group has to be distinct. There has to be a law of composition, and then it has to satisfy four properties. So here we say it satisfies the first property, that is the set is closed under the law of successive transformations. So that is the law, and the crucial property, the first property. Second one, we can define an identity transformation Okay, we can always define an identity transformation which leaves the system unchanged. Okay, which leaves the system unchanged, and this belongs to the set. Okay, so we can always define an identity transformation. So that transformation, identity transformation, does not do anything to the system. Okay, which leaves the system unchanged. There is no change in the system, and this obviously belongs to the set. So identity element is there. Now, given a symmetry transformation, we see that there exists an inverse transformation which also belongs to the set. That we will see. For any transformation, there is an inverse transformation which also belongs to the set, the third property. Finally, the successive transformation of the system obeys the associative law. It obeys the associative law. So this proves that the set considered is a group. Okay, the set that we are considering is a group. So all the four properties that a group has to satisfy, that requirement is met. Now, the group of, so such a group, the group of symmetry transformation of a system, that is called the group of symmetry of the system. That is called the group of symmetry of the system. Okay, so far we were just explaining this in words, what is symmetry transformation, or what is a group of symmetry transformation. We now explain it using an example. We consider group of symmetry of a square. Okay, we are taking a square. Okay, and we consider all symmetry transformations of a square which leave the system invariant. Okay, which leave the system invariant. Notations used. We will be having rotations, reflections, etc. Okay, that we will see. If a rotation through an angle, okay, we will be actually using rotations and reflections for the symmetry transformations. Now, if a rotation through an angle 2 pi by n, 2 pi is complete rotation, 360-degree rotation. 2 pi by n is a positive integer, about some axis leaves the system invariant. Then that axis is known as the enfold symmetry axis of the system. Okay, that is known as an enfold symmetry axis of the system. Okay. The corresponding operation is denoted by Cn. Okay, the corresponding operation is denoted by Cn. So, its integral powers, Cn square, Cn cube. This will be symmetry transformational system, which also will be symmetry transformational system, and denoted by Cnk, where k denotes successive operations of the Cn on the system. Okay, successive operations of the Cn on the system. Cn is what? 2 pi by n. And Cn to the power k, that means successive operations of Cn on the system, or 2 pi by n into k. You can rotate a system by 90 degree, then 180 degree. 180 degree rotation is actually performing Cn rotation through 90 degree 2 times. Okay, that we will see. Then there is a reflection in the plane, in a plane that will be denoted by either m or sigma. Okay, we will be using either m or sigma for that. Okay, with a subscript specifying the plane of reflection. Okay, and the identity transformation will be denoted by E. Okay, so we are going to use some notations like Cn. C is for rotation. N stands for the positive integer, which gives a symmetry transformation under rotation, which is 2 pi by n, 2 pi by n angle. So rotation through 2 pi by n angle, where n is a positive integer. So that is denoted by Cn. Okay. Then if you do this rotation successively, that will be denoted as Cn square, Cn cube, okay, etc. Then a reflection is denoted by m or sigma, and there will be an appropriate subscript. Okay, the identity transformation, which is no transformation, that will be denoted by E. Okay, now when we consider this example of a square, this will be clear to you. We are taking a square. Its four corners are marked as A, B, C, D. Okay, so the first operation, the identity operation, which gives no transformation. There is no transformation. The square remains as it is. Then consider C4. C, we know that's a symbol that denotes the rotation. Okay, so a clockwise rotation through 90 degree about an axis, normal to the square. Okay, clockwise rotation through 90 degree about an axis, normal to the square, and passing through the center. Okay, that is denoted by, see, we are rotating through 90 degree. This is the system, the square. So we are rotating it through 90 degree in clockwise direction. So this A here goes here, A here, that goes here, and B reaches here, and C reaches here, D reaches here. So this is the rotation through 90 degree about an axis, normal to the square, and passing through the center. Now a rotation through 180 degree about the above axis. 180 degree, you are giving 180 degree rotation. So A here will reach here. A at the corner 1, that will reach the corner 3. Okay, A here will reach the corner 3. B at the corner 2 will reach corner 4. Okay, so you have this 180 degree rotation through 180 degree. That is again a symmetry transformation because it leaves the system invariant. Now rotation through 270 degree. Okay, so A in corner 1 reaches corner 4. Okay, then the rotation through 360 degree, you get back the same thing, and that is same as the identity element. So identity element is either no rotation or rotation through 360 degree. Okay, then see the symbol for rotation through 90 degrees, C4. Why C4? Because 90 degrees 2 pi by 4. Okay, 90 degrees 2 pi by 4. So the symbol is C4. Here the symbol is C4 square. Okay, what is C4 square? You are performing this rotation through 90 degree 2 times. So that is C4 square. So you get 180 degree. Then we have the C4 cube here. This is rotation through 270 degree. So you are performing this C4 operation 3 times. So this is the, I think you have understood what the meaning of this symbol. C4, 4 means 2 pi by, okay, here 2 pi by n, 360 by 4, 360 by 4 is 90 degree. Okay, so we are giving a 90 degree rotation here. So it is C4, 180 is C4 90 degree rotation 2 times. Okay, now mx, that is reflection in the line 5,7. So we are giving a reflection in the line 5,7 along this line that is shown here. So D will go to the position of A, C will go to the position of B, or the element at the corner 4 will go to 1, element at corner 3 will go to 2, like that. So that is reflection along 5,7. Then there is reflection along 6,8, that's Y direction. So what will happen along Y direction means B at corner 2 will go to corner 1. So A in the corner 1 will go to 2, like that. Okay, so Mx my sigma u, a reflection along line 1, 3. It's along the diagonal. Okay, along the diagonal. So A and C will not change, but B and D, that will change positions, and reflection along line 2, 4, the diagonal, that will keep B and D in their positions, but C and A will interchange their position. So we have seen 1, 2, 3, 4, 5, 6, 7, 8 transformations. In this, one is identity transformation. The rest is either rotation or reflection. Okay. Now this can be verified. It can be verified that the set of these transformations above is a group. Okay, this is a group, which is a group of symmetry of the square. Now let's see the top operation of C4 followed by sigma u. So sigma u, sigma 4, the square. This is actually sigma u C4 means first you have to operate C4, then sigma u. So when you do the C4 operation, you will get this, and then for sigma u, you will get this. And this one that we are getting is actually mx this. Okay. So if you successively operate sigma 4, sigma u, the square that you get is mx, the original square. So that means sigma 4, sigma u, sigma 4 is equal to mx. Okay. And similarly, C4 cube C4, we are giving C4 cube C4, that is equal to E, C4 cube C4. First you give C4, then C4 cube, so you get E, so C4 cube C4 is E. Okay. Also we have C4 cube equal to E. So we can say C4 is the inverse of C4 cube and vice versa. Same way, if you take, if you give successive operations, you will get an operation in the same group. So it can be verified that each of the 8 symmetry transformation has an inverse. Okay. Finally, the transformations obey the associative law. Okay, associative law. Hence, a set of the symmetry transformations of a square actually form a group. That's the most important point to us. Set of symmetry transformations of the square, that is forming a group. We have all the elements that we need for it to be a group. It satisfies all the 4 properties. And this symmetry group of a square of order 8, that is denoted by C4V. We are denoting it by C4V. Okay. So we have seen an example where square actually has 8 symmetry transformations. One is identity transformation. So these 8 symmetry transformations actually forms a group. Okay, this is a very important thing to us all.